Hey everyone, and welcome to the Explainer. So, you've got a physics quiz coming up, right? Well, you are in the exact right place. Today, we're doing a full practice review to unpack the absolute building blocks of electrostatics. We're going to scale all the way from that tiny, annoying static spark you get in your kitchen, right up to the amazing rules of Gauss's law that literally govern our universe. I am so excited to guide you through this, so grab your notes, get comfortable, and let's get started.
Okay, really quickly, here is our roadmap for today's review. 1. The fundamentals of charge. 2. Coulomb's law. 3. Visualizing fields. 4. Dipoles and distributions. And finally, 5. Flux and Gauss's law.
Let's dive right into Section 1, the fundamentals of charge, also known as the rules of the universe. At its core, electrostatics is the study of stationary electric charges. But let's actually define what a charge is, just to make sure we've got the basics down for the quiz. Everything around us is made of atoms, right? And inside those atoms, you got positive protons in the middle and negative electrons orbiting around the outside. So if an object has a positive charge, it simply means it's missing some of its electrons. And if it has a negative charge, well, that just means it's gathered some extra electrons. Electrostatics is just looking at what happens when these charges build up and interact without flowing in a continuous current.
Now, you know what's really wild? A massive thunderstorm and that tiny zap you get in the kitchen are like the exact same thing. During a storm, lightning is basically a giant visual display of electric field strength violently neutralizing itself. On the flip side, think about shuffling across your kitchen floor in your socks and then reaching out to grab a metal fridge handle. Zap. That static shock happens when you touch metal because metal is a conductor, which just lets all that charge you built up suddenly jump. But here is the golden rule for both the lightning and your fridge. Like charges repel each other, and unlike charges attract. It's literally the binary rule of the universe.
So that brings us to the three pillars of electric charge: additivity, conservation, and quantization. These are the absolute, unbreakable ground rules of reality. Additivity just means charges add up like normal numbers. A +2 and a -3 gives you a -1. Simple enough. Conservation means charge cannot be magically created or destroyed. It just gets shuffled around. And finally, quantization. Think of an old-school abacus. Charge is quantized exactly like those wooden beads. You can't have half a bead, right? The total charge is always a neat, whole integer multiple of the fundamental electron charge. Moving right along to Section 2, Coulomb's law of interaction, the mathematics of force. This interaction was actually first measured by a French physicist named Charles-Augustin de Coulomb. And Coulomb's law takes that basic idea of attraction and repulsion and turns it into a precise math equation. The force is proportional to the two charges multiplied together. But here's the crucial part for your test. Notice the r squared at the bottom of the formula? That means the force gets weaker by the square of the distance as the charges move apart. So if you double the distance between two charges, the force doesn't just cut in half. No way. It drops to 1/4. Now, obviously, this force doesn't act the exact same way in everything. We've got conductors and insulators. Think of conductors, like metals or even the human body, as having totally unlocked doors. The electrons are highly mobile and free to move, which is exactly why a metal door handle gives you that static shock. Insulators, on the other hand, like glass, wood, or the rubber on your shoes, are like locked doors. The electrons in those materials are rigidly bound to their atoms and stuck in place. Okay, on to Section 3, visualizing electric fields. We are going to map the invisible. For the longest time, early physicists were totally stumped. Like, how does charge A actually know charge B is sitting right there? They honestly just assumed it was instantaneous magic, calling it action at a distance. But then Michael Faraday had this massive breakthrough. He realized a charge actually creates a real physical environment, an electric field, that travels outward at the speed of light. It's not magic at all. It's a completely real, invisible web spreading through space. And this brilliantly explains why that inverse square rule from Coulomb's law is a thing. Imagine the electric field strength is like light shining from a lamp in your living room. If you hold a book right up close to the lamp, it catches a ton of light. But if you move the book twice as far away, that exact same amount of light has spread out over a much wider area, right? Making the page way dimmer. Electric fields work exactly the same way. The drop in force happens purely because, as the area of influence expands, those invisible field lines have to spread out over a drastically larger space. Let's zoom out a bit for Section 4, dipoles and charge distributions. Scaling up. All right, so first up, meet the electric dipole.
This is just a pair of equal but opposite charges separated by a tiny bit of distance. Now, even though their total net charge cancels out to zero, their slight physical separation means their electric fields don't totally cancel out. You can picture the field lines connecting them as invisible rubber bands, constantly trying to pull the positive and negative ends back together. But because they are physically locked at a set distance, it creates what we call a dipole moment.
So what happens if we drop that dipole into an external uniform electric field? Well, because the positive and negative charges get pulled in opposite directions, it creates a twisting force, which we call torque. A super helpful comparison here is water flow. Imagine dropping a stick into a fast-flowing river. The current of the water is instantly going to catch both ends of that stick and twist it around until it points perfectly parallel with the flow of the river, right? Well, a uniform electric field twists our dipole in the exact same way. Now, when we zoom out to everyday macroscopic objects, we completely stop trying to count trillions of individual electrons. It's just too much. Instead, we use continuous charge distributions. We look at how charge is spread out, whether it's stretched along a one-dimensional line, painted across a flat 2D surface, or filling up an entire 3D volume space. It just makes the math of big things so much more manageable. Finally, we hit section 5, flux and Gauss's law. The geometric reality. First off, what even is electric flux? Simply put, flux is a measure of how much of that invisible electric field is actually punching through a specific area, and it heavily depends on the angle. Think of holding a bucket out in the rain. You're going to catch the absolute most water when the bucket is straight upright, pointing directly into the rain, right? But if you tilt it at an angle, way less water goes through the opening. Flux is just measuring that exact angular penetration, but for electric fields. Now, Gauss figured out something truly amazing. Gauss's law states that the total electric flux exiting any closed surface, and it literally doesn't matter how weird or lumpy or potato-like the shape is perfectly proportional to the net charge locked inside of it. It's purely geometric. Incidentally, understanding how shapes affect electric fields is exactly why lightning strikes trees during outdoor storms. The electric field concentrates super heavily around tall, sharp points like branches. It gets so overwhelmingly strong that it basically breaks the air's insulation, drawing the lightning strike right to the tree. All right, here is the grand finale for your quiz prep. We can actually connect all these math concepts together. If we apply Gauss's law to a perfectly round sphere, substitute in the geometric area of a sphere, which is 4 pi r squared, and then just rearrange the variables. Guess what happens? We perfectly derive Coulomb's law. The ultimate plot twist of electrostatics is that Gauss's law and Coulomb's law aren't even different rules. They are literally just two different languages describing the exact same physical reality. So, as we wrap up this explainer, let's do a quick recap of the 3 main concepts for your test. Number 1, charges follow strict fundamental rules of attraction, repulsion, and quantization. Number 2, they communicate this force by creating electric fields that spread out through space just like light from a lamp. And number 3, Gauss's law beautifully links the geometry of any surface to the charge trapped inside it. Now, for your challenge question, thinking about friction transferring electrons, why do you think rubbing your socks on a carpet builds up such a massive charge? And why does it just stay there until you touch a conductor? And furthermore, if Coulomb's force and Gauss's geometric flux describe the exact same reality, what else in our universe perfectly follows this profound inverse square nature? Keep thinking through those analogies. Good luck on your quiz, and I will see you next time.